Okay, welcome back everyone. In this video, we're going to continue talking about work and energy by introducing the work-energy theorem and also discussing power. So we have a few things that we want to get out of this lesson. We want to think about what kinetic energy is and how to describe it. What's the relationship between the work done on an object and its change in KE? And why is it important to use the work-kinetic energy theorem when forces aren't constant? Finally, how is the power related to work? So first we want to talk about net or total work. Now an object can be subject to many forces at the same time, and if the object is moving, we can find the work done by each force individually. For example, you could have an object on a ramp that has a string attached to it. And maybe it's a rough ramp. So you could have gravity and friction and tension, and maybe there's a spring on the other side. So you could have lots of things doing work. You could have positive work by one thing, negative by another, and zero work from a third. So what we do is we say that the net work is the scalar sum of the work done on an object by all forces acting upon the object. So the net work is the sum of the individual works. We can also equivalently say that the net work is equal to the net force times the overall, or dotted with the overall displacement. Okay? And we can show this mathematically because this combines the individual over I, Fi dot di, and that's going to turn into the net force, all acting over the same displacement. So the work-energy theorem is very important, and it tells us that the net or total amount of work done is equal to an object's change in kinetic energy. So you can see that I used some pretty big font. So when the net work is positive, the kinetic energy will increase, an object will speed up. When the net work is negative, it'll slow down. And when there's no net work acting, the kinetic energy will be unchanged. So if you think back to a couple of videos ago, we did an example problem of the falling raindrop or the sled getting dragged, and those were going with constant speed. And they also had zero net work on them. So this kind of introduces how that works. Okay, so let's just take a moment to discuss kinetic energy, which is one type of mechanical energy. It's due to the motion of an object. So kinetic energy, K, is 1/2 mv squared. Kinetic energy is in joules, mass is in kilograms, and speed is in meters per second. Okay, and in vector form, you can write it as K is equal to 1/2 m v dot v. So just in two dimensions, v is vx I hat plus vy j hat. So v dot v is actually vx squared plus vy squared, which is v squared. So there you go. The magnitude of, I should say. Okay, so that's the magnitude of v dot v. Okay, so as an example, a net force of 320 newtons acts over 1.3 meters on a 0.4 kilogram particle moving at 2 meters per second. What's the speed of the particle after this interaction? We start with the work-energy theorem. The net work is equal to the change in kinetic energy. And we realize that change in kinetic is equal to K final minus K initial. Okay? Now we don't know everything about the situation, but we do know that it has a V initial, so it does have a K initial, right? Now the work turns into F net d cosine theta, and change in kinetic will be K final, which is 1/2 mv final squared, minus K initial, 1/2 mv initial squared. Okay? Now F net is 320 newtons. The displacement is 1.3 meters. And because we don't have any other information, we assume that they are parallel to each other, so the cosine is 1. And then we just plug in 1/2 times 0.4 times v final squared minus 1/2 times 0.4 times v initial squared. We solve that for v final, and it's about 45.7 meters per second. Okay, so that's a pretty simple example because we were just given the net force. In other examples, we might need to calculate it. Okay, so now let's calculate the kinetic energy change of a 3 kilogram object that changes its velocity from v initial to v final as given there. How much net work is done on this object? Okay, so the total work done is equal to the change in kinetic energy. So the kinetic energy change is synonymous with net work, and that's going to be K final minus K initial. Okay, now we're going to use our definition from before, so this is 1/2, but it's going to be, instead of v final squared, they're vectors, so it's v final dot v final minus v initial dot v initial. Now how can I write it like that? Well, that's 1/2 m v final dot v final minus 1/2 m v initial dot v initial. So I can just factor out the 1/2 m. Okay? Then we think about this, and if this is v initial, okay, so v initial dot v initial, which is also the magnitude of v initial, that looks like it's going to be 2 squared plus 2 squared plus 1 squared, so 4, so that's going to be 3, right? Is that right? Okay, well, we want actually this squared version of that, sorry. So we actually want that to be 9, okay? That's going to be 9. Okay, v final dot v final is going to be 1 squared plus 1 squared plus 2 squared, and that looks a lot like 6. Then we plug in 1/2 times 3 kilograms times 6 minus 9 meters per second squared, and we get negative 4.5 joules as the net work, which is also the change in kinetic energy. Okay, so let's try another example. And in this one, we have forces given in unit vectors. We have a mass of 1 kilogram, which begins at rest, so we know v initial is 0. And we want to find the speed of the object after it's moved a distance of 3 meters. So now we know that the net force is going to be the sum of these two forces. We know that from last unit. And so that's going to be 4i hat minus 3j hat. And we also know that work is equal to F net dotted with displacement times the cosine of the angle between them. Okay? Now we can assume that the cosine of the angle between F net and D is going to be 0 because V initial equals 0. So if I have an object and I apply a net force to it, well, that's the direction it's going to move. However, if it had a V initial in a different direction, then it would be more complicated. Okay, so that's why we had to say that VI is 0. So the cosine of this turns into 1, and the net work is going to be F net dot D. Now F net, the magnitude of that is 4 squared plus 3 squared, square root is just 5 newtons. And the distance that it travels is 3 meters, so that's going to be 15 joules. But that's going to be equal to the change in kinetic energy, which is 1/2 m v final squared minus 1/2 v initial squared, which is 0. Now it's a 1 kilogram object, So basically V final is going to be the square root of 30, which is about 5.5 meters per second. And again, the key to this problem was realizing that V initial is 0, otherwise it makes it a lot tougher. Okay, now let's take a moment to talk about power. Power is just the rate at which work is done. If we run up the stairs, we're going to have a high power demand because we're going quickly. But if we walk up the stairs, the power demand is less. And one way to think about this, so this is the rate at which work is done, is that power is work per time. And just like we can have average speed and average acceleration, we can have average power and also instantaneous power. Okay, so if I had a graph of work versus time, and I wanted the power at a certain point, I would take the slope. dw dt would give me the power. Okay, so the limit as dt goes to 0 of the slope. Now it's also true that the power is F dot V. So how do we get that? Well, we know that work is F dot dx. Okay, or d work is F dot dx. And one thing that you can do is if you take the time derivative of each side of this, well, that's power is dw dt, but dx dt is just average velocity. Okay, so power is another scalar, and this is actually V average. So the units of power are watts, which is joules per second, or foot-pounds per second in English units. And horsepower is 746 watts is 1 horsepower. So horsies are pretty strong. Okay. So here's a silly example. We have a 1,000 kilogram space probe that lifts straight upward off the planet Zombie, which is without an atmosphere, at a constant speed of 3 meters per second. What's the power expended by the probe's engines? And we know that the acceleration is 1/2 that of the Earth. Well, power is just work over time, which is just dw dt, which, as we said earlier, is F dot V. So the force is mg, and the average speed is just 3. So we plug in 1,000 times 4.9 times 3, and that's going to get us 14,700, and we're going to have kilograms times meters per second squared times meters per second, otherwise known as 14,700 kilograms meters squared per second, which is watts. You can also write that as 14.7 kilowatts. Those are synonymous. Okay, here's another quick example. Let's say that we have quadratic air drag given by BV squared. We want to develop an expression for the power output of a plane cruising at a constant speed v. All right, well, power is just F dot V. Okay, and so we can just kind of take an average here, and we can say that it's approximately equal to BV cubed. Okay, so if we want to increase the airspeed by 25%, then that means that V turns into 1.25 V, which means that the power must turn into 1.25 power cubed, because power seems to depend on V cubed. Okay, let's do one more example. And this one has to do with how we buy energy. So when you buy energy, you're actually buying it by the kilowatt hour, which is a weird unit until you consider if power is watts over time, or work over time, sorry, then work is actually power times time, and that is kilowatts for power times hours. So a kilowatt hour is actually a unit of energy. Okay, and they'll usually charge you a certain amount per kilowatt hour. So that's really the rate that we typically see. Okay, so let's find out how many joules there are in a kilowatt hour. So 1 kilowatt times hours is actually 1,000 watt hours. But now let's convert that. And we know that 1 hour is 3,600 seconds. And we also know that 1 watt is the same thing as 1 joule per second. So these seconds will cancel, these hours will cancel, and these watts will cancel to give us that 1 kilowatt hour is equal to 3.6 times 10 to the 6th joules. And that's a significant amount of energy. Okay, so we're going to stop here. Next time, we're going to start talking about conservative and non-conservative forces and conservation of energy.